All right, so can you guys see my screen now?
Yes, sir.
All right, so last meeting we were able to finish the instrumentation amplifier. So now we're going to talk about integrator and differentiator amplifier, right? But before integrator and differentiator amplifier, let's talk about capacitance first. So maybe most of you know what is the functionality of capacitance already, but to those who doesn't know, so here's the concept of a capacitor or capacitance. So capacitance can be defined as the measure of a capacitor's opposition to changes in voltage. So the greater the capacitance, the more the opposition. Okay. So let me just give you a quick scenario for this opposition. So what do you mean by opposition? So for example, your input is a sine wave. Okay? We have this sine wave. Actually, this one is a half wave sine wave. Okay. So as our input goes up, okay, it also goes down, right? And as you can see in here, it reaches the zero voltage. But if we have a capacitor in our circuit, okay, it won't reach the zero voltage. Instead, it will give you a voltage, okay, or a current. So it opposes the zero voltage. Instead, it gives you a voltage, right? So this is like a battery that it will give you a supply once there's now out of a voltage in your circuit. Okay, so it's like a backup battery in our circuit. So capacitors oppose voltage change by creating current in the circuit. So that is they either charge or discharge in response to a change in the applied voltage. So the more capacitance a capacitor has, the greater its charge or discharge current will be for any given rate of voltage change across it. So the equation for this is quite simple. Okay, so we have this equation right here. For you to be able to get the current, it's equal to the capacitance times the derivation of your voltage divided by the derivation of time. So time here matters because how long will it, let's say, rise, and then how long will it fall? Okay, just like this one. How long will it rise? Like for example, let's just assume that this one will run for 5 milliseconds. So at half of it, it reached the peak voltage at 2.5 milliseconds, and then at 2.6 milliseconds up to 5 milliseconds, that is the falling part of your input. Okay, so that is why we have here the time divided by the voltage. Anyway, it's just the concept. So imagine if you're confused about capacitor, imagine this one as your backup battery when there is a loss of current or voltage in your circuit. All right, so let's now move on to the integrator amplifier. So this one is actually super simple. Okay, so as you can see, this is the circuit of the integrator amplifier. So if you're going to take a look at this one is actually an inverting amplifier. Very look alike. It's just that instead of having a resistor here, we have a capacitance. Okay, so an integrator, or by replacing the feedback resistance in the call this one inverting amplifier with the capacitor, we now have an RC network. So we have the R in and then the capacitance network connected across the operational amplifier's feedback, but producing another type of operational amplifier circuit, commonly called an op-amp integrator. So if you change this one from feedback resistors to capacitance, then you are now creating, or you are now making the op-amp integrator. Okay, so simple as that. So op-amp integrator is an operational amplifier circuit that performs the mathematical operation of integration. That's why it's called integrator. So that is, we can cause the output to respond to changes in the input voltage over time as the op-amp integrator produces an output voltage which is proportional to the integral of the input voltage. So in other words, the magnitude of the output signal is determined by the length of time a voltage is present at its input. Okay, so in here, the length of time of a voltage is very important. Why? Because we're using a capacitor. And also, the charging time and then the discharging time of your capacitor is, of course, depending on its value. Okay, the higher the capacitance, the more that it will oppose your output. The lesser the capacitance, the more that it will not do anything or it will not change anything to your input and output. Right. So here's a continuation for the integrator amplifier. So basically, this one is just an explanation on why we're having uh, like a shipment from the input to the output voltage. Okay, like what is the difference between the output and how did it become like this to the output? Okay, so I will leave the reading part with you guys, but here it's just explaining. Explaining that uh, the time that it will go up and then go down will be affected due to the capacitance. Okay, so yeah, basically here's the formula on how to get the voltage output if you want to do it manually. If ever, let's say you have the voltage input, you have the R in, the value of the capacitance, the value of the uh, what else? The frequency, and so on and so forth. Okay, but we can also use this one. Okay, this is the simplified formula of this one. So instead of using a derivation, so you can just use this one. Okay, so W here stands for 2 pi f, and the output voltage V out is a constant 1 over RC times the integral of the input voltage V in with respect to time. Right? So that's how you calculate the V out if you're going to do it manually. So here are some applications and advantages of an integrator. So the main use of an integrator with this circuit is with the analog computers or analog digital converters and a wave shaping circuits. So we cannot or I cannot show the examples of analog computers to you since we don't have a system wherein we're going to be needing an integrator circuit and then uh, show the output on the computer. So the only thing that we can do right now using our LT Spice is the wave shaping circuits. So with the use of integrator, we can actually control the shape, the output or the outputs of your circuit, okay, or of your waveform. So a common wave shaping use is a charge amplifier, and they are usually constructed using an operational amplifier, though they can use high gain discrete transistor configurations. So any op amps can actually do it, but of course there is a cons wherein you're going to get a very high gain, like an infinite gain. Okay. Another one here is an integrator circuit produces a steadily changing output voltage for a constant input voltage. Like if you have a changing output voltage, so you can use the integrator to stabilize your output. Okay. So you can see that integrator is also a stabilizer. All right, so let me show to you guys this one, capacitance, and then resistance. All right, so I will put this one aside for now. So this is the circuit. Okay, this is the circuit of the integrator. So we have a 1 volt input at 1 volt input at a 60 hertz, and then we have here uh, input resistance or R in, which is equal to 1K, and then we have here the capacitance, which is equal to 0.01 micro farad. And then we have here the real voltages, so 100 volts peak to peak, and then 100 volts for the negative. And this one is running for 50 milliseconds. Okay, so I didn't show to you guys the step by step on how to do this one, since this one is very similar with the inverting amplifier. Just change this one into a capacitance. All right. So for now, let's take a look. What is the output of this one? Why is there so many? Oops. All right, so we have an input of course, 1 volt peak to peak, positive and negative. And then if you're going to check here the out, we have here uh, negative 100 volts to positive 100 volts. So as you can see, this is already the maximum limit of our real voltage or power supply. So as you can see, it's not usable. So this one is similar with the op amp, or just an op amp, or an open circuit op amp, due to a very low capacitance. Okay, so if you want to control your voltage, then you have to put here a high capacitance. So from 0.01, let's make it to 10 microfarad. So as you can see here, just by changing the capacitance, uh, of course, this one now requires a higher charging time and then discharging time. So as you can see, we have positive 1 volts for the input, and then for the output, we have almost half, like 0.5 volts, and then going back to like at least 0, I guess. So it says here negative point, negative 18 actually, but this one is almost close to 0. Okay, so maybe you guys are wondering, sorry, why is it only giving us an output of negative only? That is because this one is connected to the inverting amplifier, and as usual, this one has a negative formula on it. Okay, so that is why we have only negative uh, outputs. All right. So for you to be able to control this kind of output, let's say you want to have a positive and negative output. Okay. We have here a circuit called, where is that one? Okay. We have here a circuit called the AC Op Amp Integrator with DC control. So all we need to do is just add this one. Okay. This resistance on the top of the capacitance. So let me just connect this one again. And then let me just bring back this one, the value of capacitor to 0.01. Right, so this is the original, wherein this value 0.01 micro, it's like the minimum capacitance that we can put in here. It's like we're not changing the value of your input going back to the, or going to the output. Okay, so let's see. So we have here an input of 1 volt, and we have here an output of negative 10 volts. So how did we get this negative 10 volts peak to peak? So as usual, if you have positive inputs, you have negative outputs, since this one is like uh, inverting amplifier. Okay, so as you can see right here, we only have RF and then Rin. And then as you can see, this one is the minimum value of capacitance. So if ever that you change this one, then there is a change uh, output on your waveform already. So we will not change this capacitance value. So the only thing that we will change is the feedback resistance and then the Rin. So going back to the formula, so to get the gain, we have this negative R2 divided by R1. So as you can see, we have 10K here and then 1K. So 10K divided by 1K is 10. So we have a gain of 10. So multiply that 1 to our input. So that is why we have uh, 10 volts, or negative 10 volts or positive 10 volts peak to peak. Okay. So that's our multiplier. So if you're going to put here 5K, then we have a gain of 5. So it's like our multiplier of our voltage output. Okay, so you will get here a peak to peak 5 volts to negative 5 volts. Okay, so just by adding this resistance here, which is called the AC Op Amp Integrator, okay, so we can now have the perfect integrator circuit. Okay, or like a more controlled output of your circuit or of your input. All right. And one more thing here is no more. Okay. So I thought I put here the summary when it comes to the integrator. Anyway, so let me introduce to you your laboratory. So for your laboratory, since we can only show the output shape or the shape waveform or the changes of shape output. So that's the only thing that I will ask you to do. Okay, so for integrator, design an integrator amplifier with a voltage output shape of square wave. Okay, so you can use any kind of integrator. So we have one type here, which is the AC Op Amp Integrator. There are lots more that is related to integrator. So we even have ramp integrator. That is another concept. So yeah, I would like you guys to find a circuit, or you can use this one instead. And just by changing the sign into pulse. So if you want to get a square wave or a triangular wave, I would like you guys to make an experiment on this one. So uh, put here, let's say 100, 200, 0, 0, and then let's say 10. So I would like you guys, it's your experiment, okay? So I would like you guys to find a value for the pulse and then come up with a result of square wave. Just like what I'm asking for your integrator amplifier, okay? And then same with the differentiator amplifier. So they are basically the same concept. It's just that a different arrangement of components. Okay. So in here, I'm asking you guys to come up with a circuit wherein we have an output of triangular wave, okay, or triangle wave. So I haven't saved this one yet. I was actually looking for your uh, laboratory for this one, but I cannot find anything since they are too simple. And there's only one thing that I have to think of, which is changing of waveform. So that is why just those waveforms. All right. So do you guys have any question so far regarding with integrator? So of course we'll discuss differentiator later on. All right. So an answer coming from Mr. Eda. So let me just repeat. This one is not a usable circuit since this one's like an open loop when it comes to have a gain. Okay, it's like 1,000 millions of gains. So instead, we have this kind of integrator, call it the AC Op Amp Integrator, for us to have more control to your outputs. Right? All right, next. So we have here the differentiator. So if you're going to take a look at this one, the only difference is the uh, components, wherein the first one here is the capacitance and then the second one is the resistance. So in integrator, resistance first, and then for the differentiator, capacitance first. Okay. So differentiator amplifier produces an output signal, which is the mathematical operation of differentiation. So that is why they call this one a differentiator. So that is, it produces a voltage output which is proportional to the input voltage's rate of change and the current flowing through the input capacitor. So in ideal cases, a differentiator reverses the effects of an integrator on a waveform. Okay. So basically, this one is like the opposite of the differentiator, okay, and then vice versa. Okay, they are completely opposite with each other. So having that in mind, of course, this one also has also has a capability to change a waveform. So if you have an input signal of square, you're going to get, let's say, spike. If you have triangular as your input, you're going to get rectangular as your output. If you have sine wave, you will get cosine. So the one that I will show to you guys is sine wave, because the one that I'm asking you to do is the square wave and then the triangular wave. Okay. So we have here the circuit of differentiator. All right. So as you can see, I didn't change anything. It's just that my inputs now are different. So I have now a 10-volt input and then running at 100 not kilohertz, 100 frequency. Okay, and then a capacitance of 0.1 microfarad and then 10 kilo ohms for my uh, R1. Okay, and then one more thing here is, so let me just remove this one. So this one will run for 100 milliseconds. So we have the input peak to peak 10 volts, and then if you're going to click the output, you will get this one. Okay, so it's like a fast-paced output. So as you can see right here, we have a very fast-paced output, -4 to -1, -2 to 1, and so on and so forth. So to fix this one, go to the simulation. Oops. Edit the simulation, and then you have to set here the time to start saving data into 50 milliseconds. So at exactly 50 milliseconds, it will save the data now to our capacitance. Okay? So not at exactly 0 milliseconds. So that to avoid that, a fast-paced changing or charging and the discharging time of our capacitance. Okay, since our capacitance is super small, so this one will quickly charge and then discharge its uh, voltage or current. Okay, so to solve that one, it will only start in saving the data at exactly 50 milliseconds. So right here, okay. So it will save every 50 milliseconds to be exact. All right, there you go. So as you can see, we now have like a smoother output. So as I have mentioned in here, so if we have an input of sine wave, you'll get a cosine sine. Okay. So how did I get this cosine sine? So this one actually has a computation, but I haven't uh, showed it anymore. But you can find it on the internet. Okay. So you can find the formula, and then it will only require you the capacitance value, the resistance value, the voltage input, and then the also one the 1/2 pi for the frequency, because frequency is not given. Okay, so let's now go back to the spice. So as you can see right here, we have a sine wave upon input and then a cosine wave as your output. All right, and what else? Yeah, I guess that's it. So the only task that you need to do is come up with a square wave and then sine wave using integrator and differentiator. Right, so any question or clarification so far? Not yet. Alright. So if ever that you guys have a question, so feel free to ask me anytime. So yeah, that's it for the integrator and differentiator. Okay, so if you guys do not have a question anymore, then you guys may now go, and a blessed afternoon to all of you. Goodbye. Goodbye. All right. Goodbye and thank you too.